Welcome to Arc Salt Lake on your Wednesday morning. Time right now is 7 o'clock. We are beginning this morning talking about quantum computing. Governor Spencer Cox recently announced a Quantum Coordination Council. Don't know what that is. We're going to find out. To help us understand this announcement, what it means, and the uses for quantum computing is Utah Valley University professor and chair of computer science, George Rudolph. George, thanks for being here this morning.
My pleasure.
The shirt matches the background here, definitely.
Right.
George, let's give a basic primer for people. What is quantum computing?
So quantum computing at its basic level takes its framework, if you will, from quantum mechanics, which says that, well, in quantum mechanics, for example, we look at matter and we think matter could be in any number of unknown states until we actually do some measurements and figure out what it's composed of, what states electrons and things might be in, what energy states there are. And quantum computing uses that idea to say we want to be able to compute certain kinds of problems, optimization problems and other things, really fast. And that's the basic idea. So if you think in terms of things like probability distributions, quantum computing uses that as a framework for figuring out how are we going to search really large spaces of possible solutions to problems to come up with a solution that seems reasonable.
To the average person who's not tuned into this, you know, what does quantum computing mean for their daily life? What could it mean for their daily life?
So to bring that back a little bit to earth, what it could mean for their daily lives are things like we can find new medications, new medicines quickly. We can do some kinds of medical diagnoses faster than we used to be able to do. One of the big things that people are afraid of is in cryptography, people are worried that quantum computers will crack all of our passwords and encryption technology. And while that is a concern, it's also a driver for new research that builds quantum resistant technology as well. So those are the kinds of things I think that the average person could understand and think about. There are some other things we look at for using quantum computing for, but they're maybe a little more esoteric than those couple of areas that people have heard about.
When it comes to technology, people, sometimes they see headlines. Sometimes they don't go beyond that. Maybe they'll read an article or two, and they're just not paying attention to the daily developments here. Certainly they've heard a lot about, artificial intelligence, AI. How does AI relate to quantum mechanics? Because that has been the buzzword for the past couple years.
True. So there really are three major technologies involved in current computing efforts. One is AI and things like ChatGPT and LLMs. One is supercomputing, and the other is emerging quantum computing. And AI, at its core, is about decision-making algorithms and things like that, where you need some software, or you need a machine, or you need a system that can make decisions and adapt to different environments kind of on the fly. And but the way that it gets used mostly currently in today is for a lot of automation. So being able to do things faster. That's where AI sits. Behind that, we use supercomputers, for example, GPUs and CPUs to train models for AI. But supercomputing has a broader application in that it can compute big problems really fast. And then we have quantum computing, which is different in the sense that we need different hardware than we run classical supercomputers or laptops or other things. We need new hardware for that to see the real performance gains and the problem-solving gains. And so we have universities in Utah and throughout the country and the world working on the hardware aspects of that. And that gets very technical, and that does involve a lot of physics and engineering to make that work. And that's a fun part of the field. But the other levels of that are to bring quantum computing into the realm where it becomes a commodity item like laptop computers or ChatGPT or chatbots and those things. And there's another level of effort in software and systems to be put into making quantum computing widely available.
The governor's executive order, it's a statewide effort to accelerate research, commercialization, workforce development, and advanced manufacturing in quantum technology. How big of a deal is this, the governor's order?
It's a huge deal for a couple of reasons. In some ways, Utah is a little bit behind the curve in terms of what other states have been doing and have received federal funding for. And so one aspect of the governor's order is to put together a framework and a plan for how we can receive federal funds and other economic stimuli to build quantum computing capability within the state of Utah. The other aspect of that is because, for example, other states like Illinois, New York, Colorado, New Mexico, Texas have already been doing quantum computing things and have statewide initiatives and other things. We can actually learn from what they've done. And as the executive order says, we don't have to build from scratch. We have a lot of the infrastructure pieces throughout the state and in different universities. And the executive order is critical for bringing those together, for example, with the Nucleus Institute. The critical aspect of that is that means we have a directional plan, an organized plan, rather than several different bodies or organizations doing their own things. And that the power of having the state and couching it as an economic driver is huge in terms of what we can develop.
You mentioned different universities. Let's talk about UVU. How is UVU playing a role in all this?
So I'll answer that, but in a little bit of a roundabout way.
Okay.
So, for example, University of Utah, they're known for computing, engineering, and some other things like that. They have a supercomputer data center. And one of the critical pieces, their roles they're playing is we can take the quantum computing capability and add it into the infrastructure that they already have, which then makes it a statewide available resource for all the other universities and colleges in the state, which is fabulous, by the way. It fits right into the infrastructure we already have.
Okay.
You have Utah State that is heavy into engineering and aerospace, for example. And then you have BYU that's, they cross a few areas but work in material science and quantum software and other things. Where we feel that UVU can play the biggest role is in the workforce pipeline development.
Nice.
That is, we're not really a research institution, although we do some of that. And so what we feel like is we can fill the educational piece in a big way in terms of quantum software and other things, in physics, in medicine, in computing, and also in strategic management and business. They're the strategic management department, for example, at UVU has hired a quantum person, and they're working on how do you build a business around that and do the commercialization. So really, the short answer is in the educational piece and in the workforce development piece, we feel like UVU can play a leading role.
All right, George Rudolph, we're out of time, but that's an important role to play, certainly, on the part of UVU. Thank you for coming in this morning, talking to us a little bit about quantum computing. I know it can be complicated for most people, myself included, so we appreciate the explanation.
Thank you.